Section 12.2 continued, defining chords and their related arcs. First, we want to define a chord in a circle. A chord is a segment whose endpoints are on the circle. In the diagram circle P, I have a segment with its endpoints, point A and B, that lie on the circle. Therefore, segment AB is a representation of a chord in circle P. A diameter of a circle also has its endpoints on the circle. Therefore, a diameter is a special chord that runs through the center of a circle. A chord generates an intercepted arc. The arc related to the chord is a minor arc. In this diagram, our segment AB, which is the chord of the circle, generates a minor arc, in this case, arc AB. This is the first of three parts to Theorem 12.4. If we're given congruent circles, or the same circle, and I have congruent central angles, then that generates congruent chords. In the diagram, I have two central angles. They are both 35 degrees, therefore they are congruent central angles. They intersect at endpoints on the circle, point A and B, which is a chord, and point C and D, which is a chord. Since these central angles are congruent, this theorem tells me that the chords must be congruent. Therefore, segment AB is congruent to segment CD. Part 2. Again, in congruent circles, or the same circle, if I have congruent chords, then I have congruent arcs. Here, I have two diagrams of circles. I know that these two circles are congruent because circles that have the same radii must be congruent. Inside each circle, I have chords. Here, chord AB and chord CD. By the diagram, I know that these chords are congruent. And from Theorem 12.4, if I know the chords are congruent, then their intercepted arcs are congruent. Therefore, arc AB is congruent to arc CD. Part 3 of 12.4. Again, if I'm given congruent circles or the same circle, if I am given congruent arcs, then I know that the central angles related to those arcs are congruent. Here, I have again two congruent circles. I know that circle E and circle F are congruent because the radii are both equal. Therefore, the circles I know are congruent. Here, I am given information. Here, I know that arc AB is congruent to arc CD. Therefore, I know that the central angles related to those intercepted arcs are congruent. So the central angle related to arc AB is angle AEB. And I know that is congruent to the central angle related to arc CD, which is angle CFD. Therefore, Theorem 12.4 relates three things in a circle. Congruent central angles related to congruent chords are related to congruent arcs, and arcs are back related to central angles again. So if I know one of the three, I can link all three of them together by using Theorem 12.4. For our first example, we're given circles that are congruent. What can you conclude by using Theorem 12.4? Here I have circle C congruent to circle F. Central angles in each, A, C, B, and E, F, D, are known to be congruent. Therefore, I know that the endpoints of those central angles can generate chords. And since the central angles are congruent, the chords are congruent. Therefore, A, B is congruent to ED. And we know those segments are chords of those circles. We know that congruent chords from Theorem 12.4 generate congruent intercepted arcs. Therefore, arc AB is congruent to arc ED. What can you conclude by using Theorem 12.4 in the given diagram? In circle E, I'm given two congruent chords. The chords are AD and CB. From theorem 12.4, I know that congruent chords in congruent circles or the same circle generate congruent intercepted arcs. Therefore, I know that arc AD is congruent to arc CB. Also using theorem 12.4, if I know that arcs are congruent in congruent circles or the same circles, then the central angles related to those arcs must be congruent. Therefore, angle DEA is congruent to angle CEB. These last two examples further demonstrate that 12.4 relates central angles to chords to arcs and back to central angles. Therefore, if I know one set is congruent, I can get all sets congruent, being chords, arcs, and central angles. Theorem 12.5 states that in a circle or congruent circles, that if I'm given chords that are equidistant from the center, then those chords must be congruent. Remember, the distance is a perpendicular segment from a point to a line. Therefore, when I have chords equidistant from the center, I must have a segment from the center of the circle that is perpendicular to the chord. In the diagram, I have two segments that are starting at the center and are perpendicular to the chords. And those two segments are congruent. Therefore, this theorem tells me that if these two chords are the same distance from the center, then these two chords are congruent. Therefore, segment DC is congruent to segment AB. Part 2 is the converse of number 1. I know that if chords are congruent, therefore if I knew that DC is congruent to AB, then those chords must be equidistant from the center. Now that I know that these two chords are congruent, I could reference theorem 12.4 and find arcs to be congruent and also central angles related to these chords to be congruent. The next three theorems relate back to theorem 12.5. Here, theorem 12.6 states, in a circle, a diameter, or radius, that is perpendicular to a chord bisects the chord and its arc. Therefore, I'm given a diameter that is perpendicular to the chord. Therefore, this diameter or radius bisects the chord and also bisects the given arc. Theorem 12.7 states, in a circle, a diameter that bisects a chord, the chord is not a diameter, is perpendicular to the chord. Therefore, in this theorem, I have a diameter that is bisecting the chord. Then I know that it is perpendicular to the chord. And since that is true, that would also bisect arc DC. Finally, theorem 12.8. In a circle, the perpendicular bisector of a chord contains the center of a circle. Here, I have a perpendicular bisector of chord DC. That tells me that this segment must contain the center of the circle. And since that would be true, that would also tell me that that segment would also bisect the arc DC. In this example, they want me to find the radius of the circle. I know that RS is part of the radius or diameter of circle R. Therefore, from a previous theorem, if I know that that segment is perpendicular to chord PQ, then that segment also bisects the chord. That tells me that PS is 6 centimeters. In the diagram, I don't have a radius, but I can generate one if I create a segment from the center of the circle to a point on the circle, but I'm going to make it specifically to point P. When that happens, I have a triangle, RSP, that turns into a right triangle. Now I can use the Pythagorean theorem to generate the length of segment RP, which is the radius of the circle. Therefore, 6 squared plus 8 squared equals C squared. That gives me C squared equal to 36 plus 64 equals 100. The square root of both sides, C, equals 10. Therefore, the radius of circle R is equal to 10 centimeters. In this example, they want me to determine the length of chord MN. In the diagram, I know that radius PQ is bisecting chord MN. When that's true, that radius is also perpendicular to chord MN. Now that generates right triangle NRP. To determine the length of PR, I know that PQ and PN are both radii, therefore congruent. QR is 2. Therefore, PR is 26 minus 2, or 24 meters. Now I can use the Pythagorean theorem to determine NR, or half of our chord. That tells me that 24 squared plus NR squared is equal to 26 squared. That gives me 576 plus NR squared equals 676. That gives me NR squared equal to 100, and NR, when I take the square root of both sides, is 10. NR is only half of MN. Therefore, the length of MN is equal to 20 meters. On this slide, they want me to find the value of x to the nearest tenth. On the first diagram, I know that these two chords are congruent because the chords are equidistant from the center of the circle. The length of this chord is 16 millimeters because I know that when I have a radii that is perpendicular to a chord, it bisects the chord. And since these chords are congruent, x is equal to 16 millimeters. In this diagram, I know that the radii are perpendicular to the chords, therefore the chords are being bisected. Since part of this chord is 5 feet, the other part is 5 feet. And therefore I know the entire chord is 10 feet. When chords in the same circle are congruent, both are 10 feet, they are equidistant from the center of the circle. Therefore, x must be 4 feet. In this diagram, they want me to find the value of a radius. Therefore, what I need to do is draw a different radius. I'm going to create a radius from the end point of my chord to the center of the circle. That generates a right triangle. I know that this radius is perpendicular to the chord, therefore it's being bisected. So this part of the chord must be 8 meters. Now I'm given a right triangle, and I can find the value of that radius, which happens to be the value of x. Therefore, 4 squared plus 8 squared equals x squared. And that gives me 16 plus 32 equals x squared. X squared is equal to 48. And when I take the square root of both sides, x, or the length of the radius, is equal to 6.9 meters. In the next diagram, I want to find the distance between the center and the chord. I know that the radius is bisecting the chord, therefore this part of the chord is 4 feet. I'm given a diameter that is 16 feet long. I know that the radius, therefore, has to be 8 feet. Now I can use the Pythagorean theorem again to determine x, which is the distance the chord is from the center of the circle. X squared plus 4 squared equals 8 squared. And that gives me x squared equal to 64 minus 16 is going to give me 48. Take the square root of both sides, and I know the chord is 6.9 feet away from the center of the circle. On this slide, they want me to find the measure of arc xy. In our first diagram, we're given a radii that is going to a chord, and it's perpendicular to that chord. I know that each of the legs of that right triangle that is generated is 2 meters long. Therefore, this is an isosceles right triangle. That tells me that these angles must be congruent, and therefore must equal 45 degrees. If I generate another radii to the other end point of my chord, that will also generate a right triangle that I know is to be isosceles. And that tells me that this is also 45 degrees. That gives me a central angle that is 90 degrees. And I know that the measure of my arc is equal to the measure of my central angle. Therefore, arc XY has a measure of 90 degrees. In this diagram, I'm given that chord TV and XY are equidistant from the center of the circle. Therefore, these two chords are congruent. And in a circle, when two chords are congruent, their intercepted arcs are congruent. Therefore, arc TV and XY are congruent. Radius PU is perpendicular to chord TV. Therefore, it bisects the chord and its arc. Therefore, arc TU is congruent to arc UV. Therefore, they're both 30 degrees. That makes arc TV equal to 60, which is equal to arc XY. That makes the measure of arc XY 60 degrees.